Lesson 3-4, solving quadratic equations by factoring. This is on page 157. Now, back when you guys were graphing parabolas, one of the graphical forms took what they were calling factored form. So a times x minus p times x minus q, you could say y equals or f of x equals this. That could turn into a parabola. Okay? And now, if you set that equal to zero, oh, okay, that's what goes hand in hand with this word solving right here. Right? So you're setting equal to zero, so you can solve for what would x be. And on a graph, that would represent the x-intercepts. And flip back a few pages and see if I see, oops, get before that, like here, right here, right here. Right? So if you look at this parabola, if you see where the x-intercepts are at -2 and at 5, ooh, that could fit in where the p and the q go. Right? So you go x minus -2, that's x plus 2, and x minus 5. Right? Now this a would be a vertical stretch factor, so we just make the parabola like tall and skinny if a was really big, right? But the x-intercepts would still be the same. Okay? Now, as we're going along here through uh, this new lesson 3-4, you might see some that only have one solution. And in terms of the graph of a parabola, that would be where the vertex touches the x-axis one place. And we might get some imaginary solutions. So that'd be where the parabola doesn't actually touch the x-axis at all. So this never equals zero in terms of real numbers, but maybe in terms of imaginary numbers that could work out. All right, so we'll be looking for all that. All right, so let's start going through their examples here. All right, so you might be given an equation in a standard form, so like ax squared plus bx plus c, right? And then can you factor that, which is kind of the reverse of FOIL, isn't it? Right? And maybe this lesson you could check your answers by foiling, right? If you do FOIL, first outside, inside, last, it should bring you backwards, right? For a lot of these. Now, actually, the first example we do down here is a little simpler than that. All right, so here, I'll walk you guys through, you guys see why. So you got 12 x squared minus 2x equals x, right? And they guide you through step by step. They recommend a certain way to do this. All right, I'll do it my way. I'm sure we're pretty close to that. Right, so notice that it doesn't say y equals or f of x equals. Right, so it just says x's, that's all. Right, so see, I could subtract over this x and get it set equal to zero. I mean, that would look a little closer to this, wouldn't it? Set equal to zero and then solve for x. Right? So that's what we're doing. So subtract x from both sides. Right, and then what we got here? We got 12x squared minus 3x. Right, and then x went away here, we got that's zero. Right? Right now here I have an x squared and an x, and well, there isn't really a constant other than zero. So conveniently, this is probably one of the easiest ones to solve in this whole lesson. You can factor out an x. Actually, I can factor out 3x, couldn't I? Okay. And you don't have to worry about reverse foiling or anything like that. So I can take a 3 and an x out of both of these terms. Watch this. Okay. So what am I left with here? I've got a 4 and also an x left here. And then, well, I took the whole 3x there, so I'm just subtracting 1, and this whole thing is equal to 0. Right? Again, if you wanted to check your work, if you were to take this 3x right here and distribute it back in, you should get to the previous step. Right, so 3x times 4x is 12x squared, 3x times -1 is -2x. Yeah, okay, that works. Right? Now, of course, I'm not going to do that because that would be going backwards, but I can use that to check my work, which I just did. And so we're going to pick up from here. Right? So ignore all those pinky because we're moving forward. Right, so whenever you have two parts multiplied together and equal zero, well, that means if either piece is equal to zero, the whole thing is zero. Right? So either 3x could be zero, right? Or 4x minus 1 could be zero, or they'll both lead to the solution. In this case, x could just be zero. Divide both sides by 3, x equals 0. Right? Or, let's see, add 1. So 4x equals 1, divide by 4, x is 1 over 4. Okay? So both of these would be solutions. Okay? Or I could write it this way, x equals, and put a little curly bracket schedule of that, 0, comma, 1 over 4, right? Because I'm looking at discrete solutions for x. If I take either one of these solutions and plug it back into the original statement, it should zero out here. I'll show you guys this true. Now, if I plug in 0, 0 minus 0, obviously that'll. How about 1/4? So how about 12 times 1/4 squared minus 3 times 1/4? Yeah, that also zeroes out. Yeah, totally works. Right, so, yep, totally works right there. All right. Next example. Example 2, they call a factor a trinomial. Tri means 3. Okay, so now we're getting 3 types of terms. Oh, right. I see here. I see an x squared. I see an x term, and also there's going to be some constants, some non-zero constants floating around. So this is one we're hooked at. Do some proper factoring. Yeah. So example two, right here on page 158, got x squared minus 6x minus 9 equals 18. Right, so the first thing I think is subtract 18 from both sides to get the set equal to 0. Right, that'll be a common theme this lesson, to get everything set equal to 0. And so it gives me x squared, got minus 6x. Okay, and here I got, that's minus 27, isn't it? Is that right? Minus, yeah, minus 27. Okay, is equal to 0. Okay. Now, if I'd like to get it in this factored form, can I think of two numbers that multiply to negative 27 and add to negative 6? So you can do a little bit of trial and error, guess and check. That's a common method for this particular lesson. I'm thinking something with 9 and 3, right? 9 times 3 is 27. 9 minus 3 is 6. Okay, I need more negative. Let's try this. Let's go x minus 9 and x plus 3. I'm pretty sure that'll get us where we want. Right? Now, I can check my work by doing a FOIL. Here, maybe I'll put a little thought cloud right here. A little thought cloud. Okay. I remember FOIL could be first, outside, inside, last. Here, I'll spell that out. FOIL. Okay. So if I check my work, x times x is x squared. Outside 3x, inside negative 9x, and last minus 27. Okay? And then when I pull these two together, it gives me x squared minus 6x minus 27. Yeah, that matches the original statement, which means I did correctly factor this. So that works. Right, so we're good. Okay. Now here, sort of scratch this out because that's just a little thought file right there. I just wanted to check my work, or you can do that for a lot of these in this lesson. But now I'm going to pick up from this step, right? So now we're actually moving forward. Well, if this times this is equal to 0, then either this bit, whoops, step back, x minus 9 equals 0, or x plus 3 is equal to 0, right? If either one of those statements is true, then that would make the original statement true. So x is equal to 9, or x is equal to negative 3. Okay? Or I could write it this way with curly brackets. X equals curly brackets. You got negative 3 is the solution, 9 is the solution. Okay? And just like before, if you take either one of these and plug it back to the original statement, right, I bet this all comes out to 18. Here, I'll pick one of them. How about the negative 3? Okay. Right, so if I do negative 3, and I square that, notice the negative 3 is all in parentheses, so the negative is also getting squared. Okay? And then minus 6 times, and then negative 3, and then minus 9. This has got to be 18. If it's 18, we're good. Oh yeah, look at that. Look at that. Okay. Wait, real fast, I'll do 9, or replace the negative 3 with the 9. This should also be 18. Let's see if it is. Yeah, it sure is. Sure is. All right, so actually both of these worked. We're good to go. Good to go. All right. Example 3. Solve an equation by factoring, which is what we just did. Oh, but they got a word question here. So the equation, so this is example 3. Uh, Displacement equals velocity times time plus 1/2 times acceleration times time squared. Okay? Represents the displacement. Yeah, before I even go on, doesn't that look really, really, really similar to what we did the other day with these projectile launchers? You guys remember these projectile launchers? I had you guys take these off the balcony, fire them off. You were using a stopwatch to measure how much time it took the ball to reach the ground. And I also had you set up an equation that looked extremely much like this, but very, very, very close to this. Okay, so you could apply the quadratic formula, pick quadratic equation, and solve for t that way. And I was looking at your guys' papers you turned in, and yeah, in fact, what you got on paper, what you got with stopwatch, we're really close to alignment, right? Like 1.49 versus 1.53 seconds. I thought, yeah, that means the same thing. So just a little reminder. While I mentioned quadratic, you could actually use the quadratic formula for also any of these questions in this lesson if you weren't sure how to factor it. I might bring that up as an example somewhere here. Right, but here, let's try this out. Right, so displacement of a car with initial velocity v, where with some constant acceleration over some time interval. Right, so you've got a car that's either probably speeding up if acceleration is positive, like right, or it could be braking to a stop if the acceleration is negative. Like, right? If you plug in a negative value for A, could be. Right? And maybe at the beginning of the interval, the car was already in motion. That's what this V would refer to. Find how long it takes. All right, so we're solving for a time. Solving for a time. There's t there, there's t squared there. Yeah, this is looking quadratic. Okay? That it takes a car to accelerate from 30 to 45 miles per hour. The car moves 605 feet and accelerates slowly at a rate of 2 feet per second squared. Okay. You know what? Now that I'm looking at this, I'm realizing they're mixing and matching a bunch of units. So we're gonna have to do some unit conversion. All right. That's okay, because we've got miles per hour and we got feet per second. Okay, here. So let's do a little side thought here. We're going to come back to this. Let's figure out what are these speeds in terms of goes from that speed to that speed. Velocity, initial velocity, final velocity. How do they do that? Find how long it takes. Hmm. All right, I'm realizing now they actually gave you more information than you needed. Um, like they didn't have to tell you this final velocity, but I'll show you guys this does work out. So this is, let's say initial velocity, the little subscript for initial is 30 miles per hour, right? But let's convert that to feet per second so that all the numbers are in terms of feet per second. So we'll actually have a consistent equation. Like I know 1 mile is equal to 5,280 feet. And I also know that 1 hour is 60 minutes, 60 seconds. That's 3,600 seconds. Okay. So then hours goes away, miles goes away, and I'll have units of feet per second. So I can do that. Okay. So let's see, what would that be? I gotta find that in the calculator. What's 30 times 5280 divided by 3,600? Looking at 44 feet per second. Okay, that's the number we actually have to apply in the equation. Okay? While I'm here, because I do want to check this later and show you guys that physics is all self-consistent. I mean, I saw a physics example, say, okay, I gotta do that. Okay? Um, right, they said 45 miles per hour. Okay, can I just say times 5280 over 3,600? I can just steal these ideas, right? Okay, so 45. Okay. That, by the way, by the final equals 66 feet per second. Right? Now, hold on to that idea. We're not going to use this yet, but I'll bring that back later. Okay. But we need this 44 feet per second to have consistent units so we can actually make an equation here. That's it. So they told you the distance. The car moved 605 feet. So where the d goes for distance, I'll put 605. That's feet, by the way. Okay. Equals initial velocity. Now here's what I did all of this work for right here. Is where this v goes. I'll pop in 44. And that's feet per second. Right? Times some time. I don't know how much time. Plus 1/2. And they said the car was picking up at speed at 2 feet per second squared. That means it's speeding up 2 feet per second per second. Like if you're watching the speedometer, and it's going 2 feet per second, or actually started at 44, right? So 44, 46, 48, 50, 52, right? So every second is picking up another 2 feet per second. That's what 2 feet per second squared means. Yeah, so that's right there. All right, and then we're solving for time again. Oh no, what we're solving for shows up here not squared and here squared, but that's okay because we can do quadratic on this, right? All right, so let's see what here. How much time would it take the car to, well, speeding up at this rate, starting at this speed to go this distance, right? That's what that means. Okay. Let's see. I can rearrange this a little bit, clean this up a bit. Like a half times two is just one. Here, let me swatch this. Right? So I got t squared plus 44t. I could subtract over 605 and say that's equal to 0. Right now it's all in terms of feet. It's feet per second times seconds and so on. Right. Okay. Right, so all consistent units. Okay. So what are two numbers that multiply to 600, well, negative 605, but add to 44? Okay. Now there's probably some clean solution to this because I think this particular lesson they're trying to get like nice numbers generally. Okay. But here, this is actually a really good example of where you can actually bring in the quadratic formula if you didn't know how to solve this otherwise, which I'm kind of thinking myself. Okay. Okay, so I could solve this with quadratic and then sort of work back and just solve it that way. So watch this. I know that t equals, and it's the same thing you guys did with the projectile launcher lab. Right? It's negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, just like you guys did last week, just like you guys did with the launcher. Okay? Where we've got a is like 1 in this case, b is 44, and c is negative 605. So let's try that. All right, so time equals, I mean, this will definitely give me the answer, negative 44. But no, plus or minus, that's where I'll get two solutions, so I'll be able to factor it. Square root of, see, 44 squared minus 4 times 1 times negative 605. Okay. All right, so this is all in the radical, and then this is all in the numerator, and then all divided by 2 times 1. Okay. Right. If you see a double negative underneath the radical, it's saving some footwork in the calculator. I'll two negatives make a positive. Okay, that'll be nice. Okay. I plug this in the calculator. So open parentheses for the numerator. Okay. Can you plug this correctly in the calculator? If you have to chunk it down to smaller parts, that's perfectly fine. I'm gonna put it all in one go here. Negative 44. I'll start with a plus, see what happens with the plus. Square root. 44 squared, I'll be plus 4 times 1 times 605. Close parenthesis closes the radical, close the second parenthesis closes the numerator, and then divide by 2. Okay. So I'm getting time. Oh, look at that. It is a whole number. 11 seconds. I'll say, or now if I scroll up, scroll over, and where the plus was, I'll replace it with a minus. I'll get the other answer. Negative 55 seconds, right? Which would be backwards in time. Oh, okay. Which you can model mathematically, but physically that doesn't actually make any sense. Right? So that would not be the answer. So the answer's got to be 11 seconds. Right? That is the answer. Now I just found out with quadratic formula. Let's say somehow you figured out these two numbers by guessing and checking or trial and error, or maybe you're like Ramanujan, you see it right away. Okay, let's do t. How would this actually be? It'd be minus 11 and then minus negative 55. Isn't that like plus 55? Right? And let me check my work with FOIL, FOIL. So first, t is t squared. Here, I'll just do this on the calculator screen. You guys can get it anyway. Then outside, inside, which always go together. So let's do 55t minus 11t. That gives me, oh, 44t. Bing! It worked out. Okay. And then last term, negative 11 times 55. It's got to be this. If it is, then we're good. Oh, yeah. Oh, yeah. We are winning. Okay. So just like before, if this times this equals 0, then either t could be 11, and that would represent seconds if I kept my unit, right? Or t equals negative 55 seconds, which, well, the car didn't get there in the past, so that one doesn't make any physical sense, so we're going to cross that one out. Right, so there you go. Okay. Right. Oh, there was one last connection I wanted to make. Okay. Remember how they gave us the final velocity and we never actually used that? So supposedly the car picks up to 45 miles per hour, which I converted to and got 66 feet per second. Okay. Now here's a good physics tie-in. Okay, so my physics class, I always have this right on the board behind me. So these are some of the first equations my physics students learn. They, oh, look at this one. This is exactly what we just did, right? But there are alternate formulas depending on what information you have. So I'm going to show you guys that this does work. So how about this last one? Notice this last one doesn't mention how much time, but it says initial velocity here, final velocity here, which I want to check. Okay, it's something about acceleration and the displacement move. So we got that. Let's see if this works. Does this really give me 66 feet per second? I'm going to check this right here. Click right here. So according to physics, the final velocity squared should be the initial velocity squared plus 2 times the acceleration times the distance. Okay, if you're more interested in that, take my physics class. See that? Right, so the final velocity should it be like the square root of all this stuff? Well, that's 2ax like that. All I did was I just took the square root of both sides. Here, like solving for this vf right here. Okay, right here. Okay. So let's plug those numbers in. So the final velocity should be square root of, now the initial velocity was 44 feet per second. So 44, that's, well, feet per second. Okay, that's being squared. This whole thing's underneath the radical. Okay. Plus 2 times, now the acceleration they told us was 2 feet per second squared. So in place of this a, I'll do 2 feet per second squared. And they also told us the displacement was 605 feet. 605 is feet. Okay, so all this is underneath the radical. Okay, so this goes here, this goes here, this goes here. Okay, right now if this all works, then when I plug this in my calculator, I gotta get 66 feet per second. Okay. So let's see if it is. Square root, say 44 squared plus 2 by 605. Come on, math, be 66. Oh yeah, oh yeah. And again, math is winning. What else we got? Factor a trinomial where a is not 1. Ooh, yeah, we haven't quite done that yet. Let's try it. What if you have a coefficient in front of the x squared that's like 3? Ooh, let's try that. Example 4. This is on page 159. Let's do 3x squared plus 5x plus 15 equals 17. Okay, so right away, again, let's get this set equal to 0, subtract 17 both sides. Okay. So getting 3x squared plus 5x minus 2. So that's here. All right, now, since the theme of this lesson is factoring, let's go to that. Again, okay, if you ran into a real log jam right here, like you're guessing a check-in and nothing's working, like, it's taking forever, you could always resort to the quadratic equation, just like I did a few minutes ago, right? That'll always get it for you, right? But I'm sort of thinking it back in my mind, FOIL. Right? So, see, first, outside, inside, last. What could sort of lead back to the step? Well, I probably need an x and a 3x. So let's go 3x here. Let's go x here, right? Right. And let's see. Well, the only thing that makes two, the only like nice numbers would be 1 and 2. And it is negative, so something's negative. So I need a 1 somewhere or 2 somewhere. Now, it does matter where you put it. Like if this is 1 or this is 2 or this is 2 and this is 1, it does make a difference this time because these x's are different. So you could guess and check, and maybe I'll pick the wrong way, and I'll have to. Here, I'm just gonna roll the dice and let's see what happens. Let's say I put the 1 here and the 2 here. Okay. Okay. Now I don't know what's positive or negative yet, or even if this is correct. Maybe I have to swap that, but we're gonna see. So 3x times x squared, 3x squared. Bing, got that. Now I could do 3x times 2, which would be 6x, and I could subtract off x. I could do that. So I could put the minus here and the plus here, right? So it could be 6x minus x is 5x being, and then negative 1 times 2 is negative being. Oh, so that did work. Right? Again, it's a little trial and error. I got totally lucky. I got it on the first try. Right? Now, had I not gotten that correct, if I put the 2 over here and the 1 over here, then it wouldn't have worked when I did my FOIL check. So I have to scratch that out and start over again. Right, but this time worked. All right. Actually, I don't know why I boxed that in because I'm not actually finished yet. So this could be equal to 0 or this could be equal to 0, like either one. So I have to do 3x minus 1 equals 0 or x plus 2 equals 0. Like either one of those would give me the correct answer. Right, so add 1 over here. That's 3x is equal to 1. Divide both sides by 3. X is 1 over 3. Should be a solution. Or subtract 2. X equals negative 2. Could be a solution, right? Or if you write it with the curly brackets, x equals, and then these are your discrete solutions. You got negative 2, you got a third. So x could be either of those, next to curly brackets. That's a good way to write your answer also. Right? Again, if you take either one of these numbers, the negative 2 or the 1/3, plug it back into the original statement, I bet it makes a true statement. I bet it says 17 over here equals 17 over here. Yeah, you try that out. All right. What's next here? Um, who's this guy? He looks distinguished. Math History Minute. English mathematician and astronomer Thomas Harriot was one of the first, if not the first, to consider imaginary roots to equations. You guys remember that last week? Like the square root of negative 1? If you try that in your calculator, the square root of a negative value, calculator doesn't actually know. So, oh, denominator. Right? But we were calling that I, working with that. So, yeah, that actually probably comes from this guy right here. Harriet advanced the notation system for algebra and studied negative and imaginary numbers. It's pretty cool. Right. Right. Okay, we're talking a little bit about imaginary down here. Let's see if they bring in the imaginary. Um, okay, right. This looks like it's gonna be imaginary. Just looking at it. Okay, so let's try this out. So we've got 81. Oh wait, never mind. What am I thinking? Scratch that. All right. Equals x squared. Okay? Now, you could, if you want to, you could say, oh, well, I know the square root of 81 is 9, or I could say plus or minus 9. So you could jump straight to that and say, oh, x equals plus or minus 9, x equals plus or minus 9, or x equals, if you like it this way, negative 9, 9, right? And that would be true. That's fine, right? But if you want to use the factoring method, it says solve it by factoring. Well, there's a little more to it. So maybe I could subtract over the 81. So you can go x squared minus 81 is equal to 0. And then I could factor it like this. And I could say x plus 9, x minus 9. That's all equals 0. Okay. Now, if you check it with FOIL, so first, x times x squared, bing, outside negative 9x, inside 9x, that cancels out. And so there's no x term. There's an x squared. There's a constant. Okay, and then 9 times negative 9 is negative 81. Bing, yeah, that totally works. And then picking up from this point, you get, well, same thing we got before. X equals negative 9 from this one, or x equals positive 9 from this one. Either that would zero it out. X equals negative 9 or 9, well, curly brackets, just like we got. Okay, but this is like the factoring method. Um, Now, your book did a little bit different because they subtracted over the x squared instead, so the process is a little bit different, but you really get the same answers. All right. Factor a perfect square trinomial. Now, perfect square, that makes me think um, that graphically, this would be where the vertex touches the x-axis one place, and there's just one answer, I think. Here, let's see if that works out to just one answer. All right, so we got, and they changed it to y. I don't know why they changed it to y. It doesn't really matter, though. Maybe just to keep you on your toes. Okay. So maybe it's a y versus a z graph, or something like that. So 16y squared minus 22y plus 23 equals 26y minus 13. Okay. Well, what we've been doing all lesson is subtracting everything over again, all set equal to 0. So I'll do that here. So let's subtract off 26y and also add 13. We'll do that to both sides. So minus 26y plus 13 to keep it all balanced at both sides. Boom, boom. So I still have a 16y squared. Now I've got, what is this, minus 48, I think? Is that 48y? Okay. And then plus 336, is that 36, I think? Okay. Is all equal to 0. Okay. Ooh, now you see these are all even numbers. In fact, there's something even better than that. Are these all multiples of 4? I think these are all multiples of 4. Can I pull 4 out? Say we pull 4 out. So 16 over 4 is 4. 48 over 4 is 12. 36 over 4 is 9. Yeah, let me try that. I'm going to pull a 4 out of this whole thing. Now, you don't have to do that necessarily, but I think it's going to make math a little easier to solve. So 4y squared minus 12y plus 9 equals 0. Right? So here, if you don't know what I just did, if you were to distribute the 4 back into each of these three terms, it brings you back to this step. 4 times 4 is 16. 4 times negative 12 is negative 48. 4 times minus 36. Right, so it's the same thing. Right? Okay, but this is a little more manageable. Right? So at some point, you've got a factor, because that's the theme of this lesson. Now, I could either go 4y and y, or I could go 2y and 2y. Here's what I'm thinking. If I do 2y and 2y, which would be my initial inclination, see, 9 could either be 1 and 9 or 3 and 3. Right? See, we're at guess and check mode. Right? Again, you could break out the quadratic equation if this gets too messy, but here, I'm just going to dive in and try something. Right? I know how to end up with a negative 12y in the middle, so let's try this. Let's try 4y and y and see what happens. Okay. And then 9 I'll leave as 3 and 3. Right? Now, if I need negative 12y in the middle, no, that's not gonna do it. Here, at least I'll run through one bad example, right? Um, let's say I do minus and plus, for example. Right, so 4y and y makes 4y squared. Bing, that checks out. Now, here, if I jump straight to last, 3 times negative 3. Actually, no, I would need a. What am I thinking? That's minus. These better both be negative, right? Negative 3 is positive 9. Ding, right? But how about outside, inside? So 4 times negative 3, 4y times negative 3 is negative 12y as well. This is another negative 3y. So it doesn't actually work. So this is not correct. Right. So let's see. You could sit here and play guess and check games all day, right? Or you could run to Quadratic and let Quadratic tell you right away what the answers are. So I'm going to do that. Use an alternate method right here. So I know y equals negative b, which is positive 12, plus or minus the square root of b squared, which is like 144. The negative goes away anyway, minus 4ac, and this is all divided by 2a. 2 times 4 is 8. Okay, so try to go fast. So 12 plus root 144 minus 4 by 4 by 9. Close the radical, close the numerator over 8. So I'm getting 1.5, which, by the way, is equal to 3 over 2. That might be helpful. Right? Or if I put a minus right here, it's not or anything. It's only this. It's only this. Okay. Okay. So if y is equal to 3 over 2, so if I know y is equal to 3 over 2, that tells me if I cross multiply the 2, 2y is equal to 3. Okay, I see how this is supposed to be factored. Okay, so again, my first guess and check failed, ran to a dead end. Okay. But now that I ran it through quadratic, I see how this is going to end. So it's going to be a 2y and a 2y. Okay? In fact, these terms have to be exactly the same as each other because there's only one solution. Okay, it came out of quadratic. Actually, all this discriminant is equal to 0. Yeah. 9 times 16, 144. Yeah. 9 times 16 should be 144, isn't it? Yeah, it sure is. Right. All right, so this is 2y minus 3 and 2y minus 3. Okay, this is what's going to do it. Okay, so 2y minus 3 could be 0, or 2y minus 3 could be 0. Okay, 2y minus 3 equals 0. There's only one solution. Add 3, add 3. 2y is equal to 3. Y is equal to 3 over 2, which is what I got from quadratic. So, yeah, that factor is how it works. Okay, so we are good. We are good. That's it. That's how it works. Okay, so a takeaway here is, yeah, if you're trying to factor it and guess and check, and you're checking with FOIL and you're just running into a dead end, yeah, just hop on straight over to quadratic. It'll spit you out the answers right away, and you can just work it from there. And then, yeah, sometimes you get something like this where there's only one solution. Right? Oh, hence the perfect square. Okay, yeah, perfect square. That's what was a giveaway. There's only going to be one solution. And if you graph this, that kind of z versus y set of axes, that parabola would only touch the y-axis at one place. Okay. All right, last example, complex solutions. When I say, okay, I was looking for something imaginary. Let's say this is going to be an imaginary one. Example 7. So we got x squared equals negative 144. Now, what's the square root of negative 144? Well, the calculator won't tell you anything, so it's imaginary. Okay, you could say x equals plus or minus 12i, right? Or, I mean, that would be the answer. Or you could do this, x squared plus 144 equals 0. That's it, right? So it's a different way to start it. Okay? And you could factor it. So something equals 0. So we'll work out x plus 12i and x minus 12i. Hence, it would lead you to the same outcome. Let me show you guys that this does work. So if I FOIL this out, F-O-I-L. So F-O-I-L. First outside, inside, last. X times x is x squared. Ding. Outside, inside cancels out. So negative 12ix, 12ix goes away. And then I have minus 12 and 12 is 144, and then I squared. But I squared, you guys know, is equal to negative 1. So this is x squared minus 144 times negative 1, or x squared plus 144, which is what this looks like. Right? Yeah, so however you do it, x is equal to negative 12i and also 12i. Right. Curly brackets, discrete solutions. All right, there's all the examples. All right, I picked some out ahead of time in the book. I was glancing through the answer key real fast. I was trying to come up with some that had different types of solutions. Right, great, because we just went through a bunch of different types of examples. Okay. All right, so here, highlighted a bunch here. pick some word puzzles, so those will be fun too. All right, number one. It's on page 161. Page 161 in the book. So we got 6x squared minus 2x equals 0. Now I see two terms here. They both have an x in them at least, and they're also both even. So I can pull a 2x out. And here I got the 3x remaining and minus 1, all equal to 0. See, like if you distribute this back in, it just leads to the previous step, right, which I'm not going to do. I just wanted to check my work. So 2x could be 0, or 3x minus 1 could be 0. Either way, 0 times everything else would 0 out. So x itself could be 0, or if you add 1 over and divide by 3, x equals 1/3. Right, so there's your two solutions. X equals 0, 1/3. Those both work. Boom, done. Number 4. X squared plus x minus 30 equals 0. All right, so this looks straightforward factoring. What are two numbers that add to 1, because there's like 1x, but multiply to negative 30? How about like 5 and 6? One of them would be negative. In fact, well, if 6 is 1 greater than 5, and this is positive by 1, I'm going to do x plus 6 and also x minus 5. That should do the trick, right? Let's try some FOIL. First, x squared, bing. Outside, inside, 6x minus 5x, bing. 6x negative 5, bing. It works. So if this bit could be 0, or this bit could be 0, therefore x equals, okay, it could be negative 6 from this one, or 5 from this one. So I skipped a few steps because you guys see lots of these examples by now. I bet you guys see exactly where that's going. All right, number 7. Ooh, geometry. The length of a rectangle, draw this one out, is 2 feet more than its width. Length of it is 2 feet more than its width. Right, let's try this out. Okay, so we'll draw this one out. So if this is width, and this is length, which is equal to width plus 2. Isn't that exactly what they just spelled out with that first sentence? The length is 2 feet more than the width. Find the dimensions of the area equals 63 square feet. Okay, everything's in feet and square feet. So unlike the car example earlier, we don't have to do any conversions. So that's nice. Okay. Well, I know area is equal to length times width for a rectangle. So I'm multiplying those together. And then in terms of length, I can substitute that right there. Okay. So in place of L, I'll put W plus 2. So area is equal to W plus 2 times W. Right? And I also know the area is 63 units, like square feet. So I could put it right here. So I'm getting this 63 equals, is it okay if I distribute this W? Make that W squared plus 2W. All I did was just distribute this W into here and here, just a little distribution. Right? That. Now, just like exactly what we've been doing, subtract this over, get the whole thing set equal to 0. So W squared plus 2W minus 63 is all equal to 0, right? Now, if you're really stuck at this point, you could, again, always break out the quadratic equation. Right? Nothing wrong with that. Or you can run to this guess and check, which, I think they count to. Let's factor this. There are two numbers that multiply to negative 63. So in my mind, I'm already thinking something to do with 7 and 9, right? 7 and 9. And add up to 2. Yeah, because 9 minus 7 would be 2. So I'm thinking it'd be like W plus 9 and W minus 7. So first, W squared, bing. Outside, inside, 9W minus 7W is 2W, bing. 9 times negative 7 is negative 63, bing. It all works. So W equals, okay, now if W is negative 9, this bit would zero out, and the whole thing's equal to 0. Negative 9. Or if W is equal to 7, this bit zeroes out, and the whole thing again is equal to 0. So 7. All right, so there's your solutions right there. Negative 9 and also 7. Just like that. All right, I like that. Ooh, that was 7. Let's see, number 8. Ooh, another word puzzle. Photography. The length and width of a 6 by 8 inch photograph are reduced by the same amount to make a new photograph with an area that's half the original. By how many inches will the dimensions of the photograph have to be reduced? Right? So I'll kind of trace over the rectangle I have on the other side of this paper. Okay? And what we're doing is we're shaving away Um, the length and width are reduced by the same amount. Well, okay. I was in my mind thinking like shaving like a perimeter all the way around, but I think it'll actually be a little easier if I uh hmm, let's do it this way. Okay. Just shave the top right corner. Right. You could interpret it that way. Right. And it'll be easier to draw it that way to label what's what. Right. So 6 by 8. So maybe this right here, I'll call this, well, I'll call it length. I don't think it really matters what you call length of width. Okay. Let's call that 8 inches. I'll just label it 8. Right. And this full original width right here, width was like 6 inches. So I'll call that 6. Right. So 6 by 8. Right. And then we're shaving it away. Okay. If you want to shave the whole perimeter or something, you could draw a picture like that. Okay. And the amount we're shaving away, though, I'll call X. So like if I did the whole perimeter, I'd have to call it X over 2 and then X over 2 over here. But this way of doing it, I'm just shaving off one side. Right? So X and X. Right? Right. No matter how you interpret it or draw the picture out, it'll lead to the same equation. And I want the final area to be half the original area. Okay, so my picture I see is not really going to be the scale. I have to keep shaving this off because we want this new area to be half of the original area, right? Like I drew that scale. So I have to keep shaving off, right? Like this X could be growing, right? So I keep cutting more off and more off, right? Until this hashed in area right here is half of the original rectangle, right? Um, so how could I set this up? I could say that the original area is 6 times 8, which is 48. Okay. So the full original rectangle, 6 by 8 is 48. Okay. But the new area is going to be half of that. Okay. So the new area, I'll say A new, must be half of that. And you get that by doing 8 minus x on the side. Okay. So here, so this right here is equal to 8 minus x. Right? And then this bit right here is equal to 6 minus x. See that? Like we're starting from 6 and just shaving off some x. So 6 minus x. So if I do 8 minus x times 6 minus x, I get half the original, which is like 48 over 2. Right? Yeah, I think that's my setup right there. Right? Isn't that it? Right? So I started off with 48 square inches. Right? I want half of that, and I get that by shaving away some x from each of the length and the width. Yeah, that's it. All right. All right, so here's what I do is I'm going to FOIL this out and then subtract this over, right, and then sort of like unfoil it by factoring. That's what factoring is, right? And so we'll do a FOIL, subtract, and then factor. And so first, outside, inside, last. So 6 times 8 is 48. Uh, Minus 8x minus 6x. And then negative x, that's plus x squared. This is all equal to 48 over 2 is 24. Yeah. Right, so subtract 24 over 24 minus 24. Right. I can combine these two. So I got an x squared minus 14x. And then this would be plus 24, wouldn't it? Right. And that's equal to 0. Every single example we've done this lesson is we're getting all set equal to 0. And then we can factor. Right. And so just like all along, if you get really stuck at this point, you could break out the quadratic equation, no problem. Right, but I think we're able to figure this out. We're two numbers that multiply to 24 and add to negative 14. Okay, how about, all right, see if you did, you said, oh, what about 8 and 3? Well, that only adds to something to do with 11. How about 12, I'm trying to think of a counterexample. 6 and 4, that only adds up to 10. How about 12 and 2? Hey, 12 and 2. Ooh. What if I do minus 12 and minus 2? Oh, yeah, because that could negative 2x, negative 12x gives you negative 14x. And negative 12 times negative 2, that's positive 24. That totally works right there. Okay? Actually, here I go. Just on paper, I can write the answer. So x equals, okay? Because if this times this is 0, if x is 12, the whole thing zeroes out. If x is 2, right here, this is 2, 2 minus 2, that, the whole thing zeroes out. So x could be 2 or also 12. Um, wait a minute. It can't be. Wait. There's a trick here. It cannot be both those things. I'm being silly. Let's go back to the original question. Because, guys, look at this. x can't be anything more than 6. Like if you cut like 5.9 from each side, 5.9 is now you got like a little skinny rectangle, right? That's not like hardly anything, right? So it'd be like this, right? You can't cut more than 6. So nothing more than 6 works. So the answer is just 2. So x equals 2. There it is, 2 inches. So if you tag on, it'd be 2 inches. That's the only answer. Okay? So once you cut 2, let me show you guys that actually does work. Okay? So I'm making the claim. If you start with a 6 by 8 rectangle and you shave 2 inches off, right? Then here we go, off the outside, then it will give you an area that's half of the original. So 6 times 8, the original was 48, as we said before, right? And then if I subtract 2, this becomes 4, and this becomes 6. And that better be 24, because 24 would be half of 48. It sure is, 24. Okay? So the answer is you have to shave 2 inches off. Right. Number 11. I got 5x squared plus 28x minus 12 equals 0. Okay, this is one with a coefficient on the x squared. So, okay, so this one will be maybe a little trickier, right? But it's probably going to start out with a 5x and an x, right? And then, well, okay, there might be a lot of guessing and checking involved. Like, how do you get to 12? Is it 1 and 12? Is it 3 and 4? Is it 2 and 6? I don't know. Okay. Um, but I see this, okay, this has to be negative, this be positive. So I'm going to guess this is plus and this is minus because it might be very, very positive. I mean, sort of imagine those numbers. Like if I picked, how about 2 and 10? No, sorry, what am I thinking? Right, how about 2 and 6? Oh, actually, you know what? That would be it. That would be it. Yeah. Guys, it's got to be 2 and 6. It's got to be 2 and 6. Right. Okay. So yeah, but just by luck, I think the first thing I thought of happened to work. Okay, just watch this. 5 times x is x, 5x squared. Bing! Outside, inside. We get 5 times 6 is 30x minus 2x inside gives you 28x. Bing! And then negative 2 times 6 is negative 12. Bing! All right. Ooh, okay, so I got a little lucky there. The first thing I thought of ended up working. That doesn't always work. Okay. So if you pick like 3 and 4 here to get that 12 and the 28 wouldn't work, you could sit around and guess and check, or you could always break out the quadratic formula to get a quadratic equation, and that would eventually lead you to this thing. Oh, wait, but we got a little more to do, because 5x minus 2 could be 0, or x plus 6 could be 0. So add 2, then divide by 5, 5x equals 2, x equals 2 over 5, and over here, x equals negative 6. So x equals, and we got negative 6, we got 2 over 5. 2 over 5 is the same thing as 0.4, so take that 0.4. Okay. All right, that was probably what they're looking for right there. All right, number 17, solve by factoring. We get x squared equals 289. Now, right away, I see 289 is 17 squared. It is a perfect square. So this should come out plus or minus 17. But if you solve it with factoring, you do minus 289 is equal to 0. You do x plus 17, x minus 17 is equal to 0, right? Because first, outside and inside cancel. And the last, we should think, yeah, that's exactly it. X equals negative 17 or 17. Okay. And it was. Oh, that was number 17. They did that on purpose. Number 20. Uh, x squared plus 3 equals 124. Okay, so subtract off 124. X squared. Well, 3 minus 124 is negative 121. Okay. Oh, 121 is also perfect square. That's 11 squared, isn't it? So I think it'd be x plus 11, x minus 11 goes to 0. Okay. And then x therefore could be either negative 11 from this one or positive 11 from this one. Those would each zero out that whole bit. Okay. That works. All right. Number 21. 21. We're getting 4x squared minus 28x plus 49 equals 0. Okay. Ooh. Well, right. 49 is 7 times 7. these numbers are multiples of 4, so that doesn't have anything in common with 7. So I think we're just gonna have to straight start guessing and checking. All right. Now, is this 2x and 2x, or is it 4x and 1x? I don't know. But I'm pretty sure that 49 is probably 7 and 7. And if I'm getting negative in the middle, it probably goes -7, -7. That's my best guess. Right? So it's probably something -7, something -7. Now, now what? Um, I see what it is. It is 2x and 2x. Let's watch this. 2x and 2x. I'm doing a reverse FOIL. Okay, so I'm checking my work in my mind. I'm doing FOIL. 2x and 2x is 4x squared. Bing! 2x times -7 is -14x. And this is also -14x, which gives you -28x. Bing! -7, positive 49. Bing! Yeah, it all worked. Now this and this are the same thing. So this is the same thing as 2x minus 7, quantity squared equals 0. Ooh, so now there's only going to be one solution. If you graph this, this would look like a parabola where the vertex touches the x-axis. Here, I'll show you guys. I'll make a little graph after I finish this off. So square root both sides. 2x minus 7 could be 0. 2x equals 7. Have 7 over. X equals 7 over 2. Or 3.5 if you like. That's 7 over 2, right? Okay. So what does that actually look like? Uh, all right. So if I took the original expression, I said y equals or f of x equals, right, this original thing here, right, this is what it would do. You can try this in Desmos or graphing calculator if you like. We go 1, 2, 3, 4. 1, 2, 3, 4. Right? At 3.5, there would be a vertex of a parabola. And it would be a tall, skinny parabola because there's a coefficient 4 in this x squared term. It would be a tall, skinny parabola. Looks something approximately like that. Yeah. Okay. Okay, so where the whole thing's equal to 0, it's only one place. Okay. All right. 22. Get 9x squared plus 6x equals -1. So right away, I'm thinking, what if I add a 1 over? 9x squared plus 6x plus 1 equals 0. Okay. So it's probably like 3x something or 3x. All right, I'm guessing this is going to be 3x and 3x. Okay. And there's other ways you can get that too. This is almost certainly 1 and 1. And this is like plus and plus. Yeah, look at that. 3x and 3x is 9x squared. Bing. 3x and 3x is 6x. Bing. 1 and 1 is 1. Bing. Right, so this is 3x plus 1. Quantity squared equals 0 if you like. We're doing that step. So 3x plus 1 can be 0. There's only going to be one solution out of this. 3x equals -1. X equals -1 third. Right? Yeah. Right. Number 30. Got x squared plus 4 equals 0. Now, some of you guys might right away see this is going to be a special case. Because, guys, if you square anything, doesn't this have to come out positive? And if you add something to a positive number, that will never zero out in terms of real numbers. But what about imaginary? You could subtract over the 4 and take the square root and get plus or minus 2i. I think that's what it's going to be, right? Plus or minus 2i. Now, if you use the factoring method, then it looks like this. I get x plus 2i, x minus 2i. And that all zeros out. Okay. Let's watch the FOIL. Right, so I'll draw the FOIL tracks. F O I L. Okay, a little FOIL right there. Okay. So x times x is x squared. Bing. The outside and the inside cancel. Bing. So there's no. See the original statement. I don't see anything about I. Right. And then the last 2i times -2i. Now, maybe you see this and maybe you need to be reminded. Okay? I is the square root of -1. So this is 2 times -2 is -4. And then I squared. So I squared is -1. That subs in right there. So negative, negative cancel. It's -4, which is just 4, which is what this is right here. Yeah, so that totally works. All right, so this is just a little thought cloud. I'm just reminding you guys why this works from last week. Okay? And so really the next step is to bring this down here and say x could be equal to negative 2i from here or positive 2i from here. So negative 2i or 2i. Right, so I might write it that way. Right. You could probably also write it this way: x equals plus or minus 2i. And I would also accept that. Right. So either one of those. Right? 31. Okay, then 36 x squared equals negative 25. Huh. All right, well, add 25 over. 36x squared plus 25 is equal to 0. So this is going to be another imaginary set. Okay? All right. Well, I know 36 is 6 squared, so probably something to do with like 6x and 6x. 25 is 5 squared, so something to do with 5, right? I think it's going to turn out to be 5i and negative 5i. So like plus 5i and minus 5i. Boom, boom, boom. Outside inside cancel. 5i times negative 5i is positive 25. Yeah, that works. Right, so, well, you either have 6x plus 5i equals 0, or 6x minus 5i equals 0. Right, so 6x equals negative 5i, or 6x equals 5i, 5 by 5 by 6, x equals negative 5 over 6i, or, and then positive 5 over 6i. Right, so let's look at there. All right. Number 40, animation. A computer graphics animator would like to make a realistic simulation of a tossed ball. Of course, I saw this one. It's like, oh yeah, there's physics, there's an art connection here. Right? If you're a graphics designer one day, you're animating something, you want to make your animation look believable. And for that, I should do some physics and some math, right? And some quadratics. Right? So that the audience seeing your picture's like, oh yeah, I'm totally immersed in the story now. The animator wants the ball to follow a parabolic trajectory, represented by this equation here. Yeah. What are the solutions of f of x equals 0? Well, luckily they gave it to you in factored form. So you can see it right away. If f of x equals negative point, can I call it negative 1 over 5? Same thing. Of x plus 5 and x minus 5. Right? See, what would it take for this whole thing to be equal to 0? Well, if x is negative 5 here or positive 5 here, either that would zero out the whole equation. So that's it. Right? Um, If the animator changes the equation to this, now what are the solutions? So that was question A. Now we're question B. We're going to change it to f of x equals, again, I'll write this as a fraction of this field, given that x squared plus 20. Now what? Um, well, if we're looking for where it's equal to 0, because that's the question. Right? I could do this. Could I multiply both sides by negative 1? And that would give me 1/5 x squared minus 20 equals negative 0, which is just 0. I could also multiply both sides by 5. So watch this. I say 5 times all, like everything. 5, 5, 5. Okay. So that's x squared minus 100 equals 0 times 5 is still 0. Okay. So I'm getting x minus 10, x plus 10 equals 0. So x could be negative 10 or 10, or if you like, plus or minus 10. Okay. Okay. All right. So changes the trajectory a little bit, right? Okay. How the ball was thrown in your animation. Okay. So two more I'm going to do with you guys. Number 45, or sorry, number 44. 44. You got the rule for factoring a difference of cubes is shown below. Use this to factor this. Oh, yeah, yeah. So we're going to stretch your imagination a little bit here. So I said, hey, remember this? I don't know if you guys learned this in a previous math class. Right. So a difference of cubes is equal to the difference of the numbers, or like the roots, right? Times a squared plus ab plus b squared. That's interesting, right? How could you use that to factor something like this? 40x to the power of 5 minus 135 x squared y cubed. Hmm. Difference of difference of cubes. Okay. Now, if I want this to sort of fit this format, so that I can factor it. I bet the final answer is going to look something kind of like this, right? Um, okay, I see the y cubed that looks so kind of like this b cubed sort of. Right? Now, x to the 5, that's too many on the power, but there's also an x squared here, so I can pull an x squared out. Okay? I also see that both 40 and 135, both of those are multiples of 5, so I'm going to pull it back up. I'm going to pull a 5 and also an x squared out of the whole thing. Pull it out here. 40 divided by this 5 leaves me with 8, and then I got x cubed. Okay, so that's already looking much better, because 8 is 2 to the power 3. Yeah, I see where this is going. And then, now I don't know this off the top of my head. 135 over 5 is 27. Oh, and 27 is also a perfect cube. And I took the x squared out already. And so I'm left with y cubed. Yep. This is looking much better. Yeah. Okay. Because guys, this is the same thing as, okay, so I got my 5x squared. I just pulled that out. Okay. And then in brackets here, guys, 8 is 2 to the power of 3. So it's like 2x to the power of 3. And then 27 is 3 to the 3. So it's like 3y to the power of 3. Now I have a difference of cubes. Now it actually does match the original setup. Look at theirs. Look at theirs. Okay. So all I have to do now is just fit this format. Yeah, that's it. So still have my 5x squared regardless. Still got that. All right, and then in my brackets here. Okay, so according to this format, I should take this a cube and just make it a. So that's like a 2x. And then minus b, which is like my 3y. Right, here, let me really spell this out in peek. Okay, do you guys see that my a is like 2x and my b is like 3y? Right? So if you didn't see that before, but you see it now. A is like 2x, b is like 3y. See how it matches? It matches, right? Okay, so that's what I did right here. So this bit is like this bit, ding, same thing. And then this right here. So I need the a squared, that's like 2x being squared, plus and then ab. I got a 2x and a 3y. And then I got a plus 3y being squared. Okay, just fit that in right there. Okay. I think I could clean this up a little bit more. Like this should be a perfectly valid answer. Oops, did I? More, let's see. Okay. But let me write this one more time. Got a 5x squared. Okay, I'll keep my 2x minus 3y right here. So that's the same. Okay. And then here, well, okay. Whether you want to leave it like this or you expand it a little bit, I guess is up to you. But if I wanted to, I could call this 4x squared. I could call this 3 times 2 is 6xy. Yeah, okay. And then I got a plus 9y squared. Right? You could do that. Right? So maybe how about like that? Right? That would be the expanded form right there. Right? Yeah, all right. So stretch your imagination a little bit at the end. Right? Yeah, it's probably what they're looking for. All right, and then yeah, number four. Oh, wait, look, there's yeah, that's from last week, back when you guys were doing the projectile launchers, right? But number 45, create. Choose two integers, 45. So that's just um, so like regular counting numbers, 1, 2, 3, 4, 5, but also 0 and also negative. So negative 3 is an integer. Pi, 3.141 is not an integer. Actually, anything with a decimal is not an integer. 3.5 is not an integer, right? So negative 3, negative 2, negative 1, 0, 1, 2, 3, and so on. Write an equation in standard form, so it's like ax squared plus bx plus c, with those roots. How would the equation change if the signs of the roots were switched? Right? Well, let's come up with okay. How about two integers? How about negative 3 and 7? Negative 3, 7, whatever. Okay, so I can write the factored form like this. I could do x minus negative 3 times x minus 7. Right? Um, Now they're talking about those being roots, right? And equation and standard form with those roots. Well, maybe I'll say y equals, okay? Because if this was equal to 0, then these would be the roots. But it said write an equation, so maybe I'll say y equals. So it's y equals, that's really x plus 3 and x minus 7. Right? Something like that. Right, so what does that look like on a graph? Show you guys. Right. Got x. dot y. Okay. So if you see, if x was -3, the whole thing would zero out. If x was +7, the whole thing would zero out. Okay. Oh, I mean, that's kind of what we're starting from anyway. Okay. So I bet the graph looks. Great. Here, let me get one more point. If x is 0, is this -21? So -21 is down here. Okay, so let me go back to it. Anyway, I bet there's a parabola that looks approximately like that. Okay? And then if the signs of the roots were switched, like what if I had +3 and -7, the whole parabola would just shift this way, where it go through +3 and -7 way back here. I said that'd be a little different. All right, so yeah, there's an application right there. Factoring.